Hello and welcome to another worked example with Dr. Schleich. You can see in this question we're dealing with the concept of work done. So we'll start by explaining what is meant by work done. Let's call it W for work. The work done is the force times the displacement. So we can sort of think about it like an equation. Work equals force times displacement. So we wouldn't want to just sort of leave these symbols as our answer, though. Okay, we'd want to define each of them. Moreover, it's important to remember that the full form of this equation is force times displacement times cosine theta, where theta is the angle between these two vectors, right? So it's a scalar product or a dot product where work is a scalar, but we're multiplying two vectors to get it. And this basically means that only the component of force acting in the direction of displacement contributes to the work done. So what is meant by work done? Work is the force applied in the direction of displacement. So it's like force times displacement, but only the force or the component of force in the direction of displacement. I leave it to you to sort of put that in your own words. I'll give you a few minutes to do that. If you're following along at home, now's a good time to pause the video. We'll probably have to come back to this definition here, right? So it's only in the direction of displacement. All right, we have a car traveling along a road that has a uniform downhill gradient as shown. The car has a mass of 850. The angle to the road to the horizontal is 7.5 degrees, and we are to calculate the component of the weight of the car down the slope. All right, so the car has weight that goes straight down like this, and that weight is equal to mg. All right, so we're given the mass, and so we can calculate the weight. Well, imagine that we're here on Earth with a gravity field equal to 9.81 meters per second squared. And remember, that's the same thing as 9.81 newtons per kilogram. Two different ways to think about the acceleration of free fall or the strength of Earth's gravity field. So there's a component of this vector that's acting into the sort of ramp that way. I'm going to draw it like this. And then there's a component that's acting sort of parallel to the ramp itself. That's the component of weight that's acting down the ramp. We could sort of translate this vector here in space and sort of realize it's the component that would sort of otherwise make it speed up or sort of move down the ramp if there weren't sort of frictional forces or whatever. So we're calculating that component of weight. So this angle here is 7.5. That's the same as this angle here, 7.5 degrees. And we can see that the component of this weight vector that we're calculating is opposite that angle there. So the sine function is going to be helpful with that, right? The hypotenuse is the weight mg, and the component of weight is going to be sort of opposite the angle, and we can relate it back to the hypotenuse with the sine function, right? So we'll say that the sine of this 7.5 degree angle right here is equal to the side opposite. So that's going to be the component of weight that's going down here. We'll call it the x component of weight divided by all the weight. Now, some students would prefer to calculate a number and sort of plug in a value. Since we've got, 7.5 is a number. The variable that we're solving for here, the x component of weight that they ask us to solve for. And so let's just calculate this mg weight real quick. I pride myself on my prodigious mental math capability, and so I'll multiply this in my head and realize that it's 8,338.5. It's okay for you to use a calculator, though. And that's going to be in newtons. Don't look back here while I do my mental math, students. It makes me nervous. YouTube can't see, just just like an ink pen floating around. You guys can look and see that how I do my mental math here, my calculator. All right. Speaking of mental math, let me go ahead and calculate the sine of 7.5 degrees in my head. I think it's like around 0.13, but if I carry it out to 100 millionths place, it's like 0.130526192, something like that, maybe. Yeah. And I'll just go ahead and multiply it by 8,338.5 in my head and realize that that's, well, let's see here, 1,088.39265, no, 54, yeah, that's what it is. In my head. But we wouldn't want to report it to that level of significance just because I can calculate it out, that far in my head. We'll just round it to 1088. 1090 might be the best answer to report, but I'm going to sort of keep, 3 significant digits here, realizing that there's only 2 significant digits in this, and then even in the mass was 850. I should probably report my answer to this question as 1090. Let's take a look at how many marks that one was worth. So 1 mark for realizing that work done is force times displacement, but only the component of force acting in the direction of displacement contributes to that product. So 2 marks for the component of weight acting down. And again, the best answer to write down on this line here would be 1090, in my opinion, 1090. Full marks for 1088, but the working is what's important there, right? It's sort of like this vector triangle where this is the same as this vector, right? It's the magnitude is sort of 1088, the direction is down the slope, and we could draw it sort of opposite the 7.5 degree angle to help us sort of realize it's the sine that's the useful trig function, but it's acting on the car sort of there down the ramp. All right, the next part here says the car in V is traveling at a constant speed of 25 meters per second. The driver then applies the brakes to stop the car. Constant force resisting the motion of the car is 4,600 newtons. Let's go ahead and show that the deceleration of the car with the brakes applied is 4.1 meters per second for 2 marks. 2 marks ready to go here. All right, we're given a force, we got a constant speed, applies the brakes to the car. So if we remember that Newton's second law tells us that the sum of the forces, or the net force, the resultant force, right? All of the sum of all the force vectors equals mass times acceleration. We know the mass of the car, so that's given. We're trying to solve for acceleration, so we need to just consider the vector sum here. They give us the resisting force, right? And the constant speed is positive 25 meters per second, right? So we can say that in the direction of motion, there is a force of 1,088 newtons, right? But opposing that is the negative 4,600 newtons of braking force. So that's our vector sum. These forces oppose each other. On the diagram there, you have your car, and you've got the component of weight going down that we just solved for. When you hit the brakes, you're acting against, right? Resisting the motion, right? So that force vector is stronger. 4,600 is bigger than 1088. It's negative because this is the positive direction, right? So the component of weight that's acting down the ramp is in the same direction as positive 25 meters per second, this velocity vector. So we can solve that for acceleration there. Earlier, we were looking at equivalent sort of units, and we said that for acceleration, g, 9.81 meters per second squared, equal to a Newton per kilogram. Considering the same sort of law here, F equals ma, and reinforcing the learning objective regarding relating the base units to the derived units, an important derived unit in physics is the Newton, unit of force, but it's equal to a kilogram times a meter per second squared. So because F equals ma, then a Newton of force is equal to a kilogram meter per second squared, right? So those are the base units. If you were to plug this in for newtons, you'd realize that the kilograms would cancel and you'd have meters per second squared, which is perhaps more familiar to you for the units of acceleration like that are given here. So a Newton per kilogram does indeed give us the correct units of acceleration, or equivalent to the meters per second squared because of what a Newton is. 3512 divided by 850. Let's see, I get 4.131764707. No, 6, my bad. It's hard to do mental math all the way out to the whatever place that is. But I think it's a 6. You need to double check me in your calculator class. Meters per second squared. All right. So I'm going to go ahead at this point at 10:17 on 10/7, 2022. I'm going to retire that joke. Okay. I feel like it's sort of lost its momentum. We'll study momentum later on in the year. But all right, no more of that. My apologies. YouTube is like, no, that's our favorite joke. Leave it down in the comments below, YouTube. If you like the joke, you want to keep a good thing going, just leave it down in the comments. Maybe now's a good time to remind you to smash that like button. Don't forget to get it on the Dr. Schleich notification squad. Make the red bell gray. Turn your phone sideways so you can see that, and make sure you're clicking that bell. Okay. Check out the merch shop. No, there's not a merge shop yet. You guys have a growth mindset. We're gonna just have the power of yet. All right, so indeed, we can show that the acceleration is about 4.1, just like they said we'd be able to, but it's exactly it's more precisely 4.13176 and so on. They want us to now calculate the distance the car travels from when the brakes are applied until it comes to rest. All right, so get rid of that. Distance traveled. This sounds like a kinematics question, okay, where we know that the final speed is 0 because that's what rest is. So they don't say 0 meters per second. You have to translate this word into that sort of number. The initial velocity was 25 meters per second, right? Say the moment when the brakes were applied, it was going that fast. We don't know the time. They don't tell us the time. They don't ask us to calculate it. So maybe that's not a good way to go. We do know that the deceleration, right? Remember, positive 25 meters per second, it was a negative 4.1. I think I did have the negative sign in the force, but maybe, when you're doing the math, like, well, is the negative sign important? Here it kind of is, right? Because we're going to plug it in sort of negative relative to the positive velocity there. So in the word deceleration, right, gives us a clue that, yep, when we get a negative answer, and we're solving for deceleration, that would be a negative acceleration. So that makes sense there. So we have that, and we're solving for S. So the two unknowns are S and T. So one of the ways that we could solve this is calculate the time that it would take this to happen, and then plug that back into some other equation of motion. But there is an equation of motion that relates final velocity, initial velocity, acceleration, and distance. And if you've got good detailed and accurate notes, you could probably find this equation in there and realize, oh, that's the equation that doesn't contain time. So we don't care about time. We're not asked to solve for it. Let's just use this one. So 0 squared equals 25 squared plus 2 times negative 4 point. And here you could use like the 1, 3 or whatever, 4.13176 if I recall correctly. Or just 4.1. If you were stumped on this working here and you didn't have the more precise number, you could, still use 4.1 because they gave you that number there. That's meters per second squared. These are meters per second for velocity. Let me actually add those units in. So the units for velocity, meters per second, that whole quantity is squared, plus 2 times negative 4.17. 1317 meters per second squared times the displacement S over here. So that's what we're solving for. 25 squared is 625. So we're subtracting 625 meters squared per second squared from both sides. So that gets rid of that. And on this side, it's negative. That's equals, we're subtracting that. We still have this plus 2 times negative 4.1317 meters per second squared. Yes. All right, so now I'm going to divide each side by like this negative 8.2 or whatever. Dividing each side by negative 8.2634. And note that the units here are meters per second squared. So these per second squareds are going to cancel, and one of these meters is going to cancel. So we're left with meters of distance, which is why you kind of want to keep the units in there just to make sure that hey, I should cancel everything out with the units also. Like when I square this velocity meters per second, I'm also squaring the units, and that's how we can cancel out the square seconds in the acceleration term. So 625 divided by 8.2634 solves for the distance, and it's 75. So the calculator value that we get, yes, it's a calculator. Of course it was. It's not a funny joke, actually. All right, 75.6, and so what will we round that to? 76 meters, thereabouts. All right, so this car comes to rest after 76 meters of distance. For a bonus challenge, solve it for time, and then find another equation of motion to, get that answer. By a showing of hands, who would like to do that right now in class? All right, even though everybody's raising their hand, I'm going to just overrule you all in the interest of time. I'm just, all right, settle down. I know everybody wants to solve for time. Okay, just do it on your own. You understand me too. We want to solve it two ways. All right, clear that out. Now we need to calculate the loss of kinetic energy of the car. The loss of kinetic energy of the car. So got some kinetic energy equal to 1/2 mv squared, and it's going to go to 0, right? Because the final speed is 0. So when we plug that in, so I mean, this is pretty straightforward. 1/2 850 kilograms times 25 meters per second quantity squared. I think that would, in other words, if we calculate the initial kinetic energy, that it has before it applies the brakes, the loss is going to be all of that, right? Because it goes to 0. So that's the loss in kinetic energy. Half of 850 times 25 squared. So 25 squared is. So I get 265,625, which you'd maybe say is 266,000. Round that up to 6. 266 kilojoules, 266,000 joules. Now the work done by the resisting force, right? So this is where we started this calculation with the definition of work done, or explain what is meant by work done. So the equation that we considered was this one. Now the vectors here are in the direction of motion, right? So in other words, we were only considering sort of the component of weight that was acting down. The work done by the resisting force, I mean, that's a big clue. I mean, they already told you what it was. They're reminding you, this is the force you want to plug in. The displacement that we already solved for was 76 meters. And so that resisting force was acting on it for 76 meters, right? That's the displacement that we calculated that it would bring it to rest. Remember, the values that we used to solve for that displacement were the same values that we sort of calculate here, 25 meters per second initial velocity to 0. That's why, the proper sort of, loss calculation would be, minus sort of 0 or whatever. 4,600 times 76. So I get a calculator value of 349,600, which is really close to 350,000 joules. All right, so it loses 266,000 joules of kinetic energy, but the work done is 350,000 joules. Okay. Those numbers are not the same. Oh, didn't realize that. I'll put that back up in just a moment. Let me just do this real quick. It says the quantities in 3-part 1 and in 3-part 2 are not equal. To explain why these quantities are not equal. So that's what we're trying to consider now. 3-part 1 and 3-part 2. These are these numbers that we got here. All right. So why are these not equal? It was a car that was going down like this, 76 meters, then it was brought to rest. So 76 meters, and there was a force going against it. And so the resistive force was this much. The work done by the resistive force was 350,000, but it only lost 266,000 joules of kinetic energy. How much energy are we missing? Let's start with that. I'm going to use the 349,600 minus this number, 265,625. All right, so we're missing some energy here. The missing energy, everybody with a calculator or better mental math capability than me, 83,975 joules. I know, it was destroyed. There you go. Explain why they're not equal, because the energy was destroyed. All right, settle down, class, settle down, class. The whole class just went in an uproar, YouTube, because they know that energy is neither created nor destroyed. We didn't destroy that energy. We got to conserve it. We got to account for it. Can anybody account for that missing energy? Where is it? We might say, well, maybe like sound and heat, like there's some energy losses. Is there 83,000 joules of, sound and heat or something like that? We always, say, oh, well, it's never perfect, right? Well, we considered a resisting force. In other words, when we apply the brakes, that 350,000 joules of energy that was work done in the brakes, like where did that go? It shows up as heat and sound and things like that. So like we've already kind of accounted for those energy losses here. Right, so anybody else have an idea about maybe where there's 83,975 precious joules of energy? If it traveled 76 meters this way, and this angle was 7.5 degrees, how many people out there want to calculate this vector right here? Let's call it h for height. Everybody, awesome. So it's opposite the 7.5 degree angle. The hypotenuse is 76. All right, we could solve this by saying, well, h over here, this h for height, right? That's going to be the sine of 7.5 degrees times 76 meters. We're solving for the actual height that it's going downhill, right? It's a downhill gradient. There's your clue right there. 7.5, the sine of that times 76. That's about 10. It's 9.9199 meters down. If we know the height, we know the mass, we're on Earth, we know the height. MGH, right? There's some work done here. Gravity's doing some work on this thing. Potential energy due to gravity. So the M, 850 kilograms, the G, 9.81 newtons per kilogram, that gives us the weight of the thing, right? All of this weight ends up lower in Earth's gravity field. It had more potential energy up here, right? Let's plug in this 9.919 meters that we know that was the actual vertical displacement. Remember, this goes right back to the very first statement about explain what is meant by work done. Gravity is doing some work, but only in the direction of displacement. Gravity only affects things in that direction, right? That's the 9.8 newtons per kilogram in this direction. So height is going down. That's why this is the correct displacement vector to substitute to consider how much potential energy was converted here. The car has more potential energy, 9.9 meters up in Earth's gravity field. So the moment of truth here, 9.9199 times 9.81 times 850 equals 82,717 is what I get in my calculator. I'm going to toggle that over to negative, and I'm going to add 83,975 to it. Now I've got 1,257 joules. And those joules will forever remain a mystery. This is Dr. Schleif, still living the physics life. We'll see you next time.